All right, thank you to the organizers for all the work they've done to put this program together, and to the Institute for providing such a productive environment for meetings of this sort. Let me start by saying that I'll be compiling as we go along a sort of annotated bibliography of the various references that will come up, and some indications of things that I won't go into in as much detail in the actual lecture. At the moment, I just have this document posted on my webpage. Maybe we can eventually mirror it to the conference website. Right now, it only contains today's lecture. I'll be updating it over the course of the week as we go through the lectures. So in case there's something that went by that I didn't give too many details about, some more details will be given there, but mostly it will be references to relevant literature, including other notes of mine, particularly my notes from the Arizona Winter School in 2017. Okay, so today, the goal of this lecture is to talk about perfectoid fields, and the framing goal is to give a 21st century interpretation of a 20th century theorem. So let me start with a result from the late 1970s due to Fontaine and Winterberge, both of whom unfortunately we lost earlier this year. And I'll state this in the following way. The absolute Galois groups of the following fields are isomorphic. So if you take the field QP, like here, and so I'm not going to work directly with QP, I'm going to work with the P cyclotomic extension. So QP adjoin mu P infinity, by this I mean add all P power roots of unity. So this is an infinite algebraic extension of QP. Anyway, so its Galois group is going to be some subgroup of infinite index of the absolute Galois group of QP, but it's not so far off. So the Galois group of this thing is closely related to the Galois group of QP. So this Galois group, it turns out, is related to a Galois group of a field that lives in characteristic P. So the absolute Galois groups of these two fields are in fact isomorphic. And they're isomorphic not just, what do I mean by they're isomorphic? Well, I could just say they're isomorphic as groups. That's not a very interesting statement. More precisely, the Galois groups of fields are topological groups because they're inverse limits of finite groups. They have a profinite topology. So I could upgrade this to a topological isomorphism, say that they're homeomorphic. But what I really mean is that not only are the Galois groups of these two fields isomorphic, in some sense the Galois theories of these two fields are isomorphic. That is, there is an isomorphism of the subfield lattices, of the field lattices, within some pair of algebraic closures. So there is some way to match up finite extensions of this thing within some algebraic closure and finite extensions of this thing within some algebraic closure so that all the inclusions align. Yes? Not for the statement about Galois groups. I'll make that comment in a moment. That won't change the Galois group. Obviously, when we talk about perfectoids, we will want to work with perfect fields, but the statement here as written is still correct. Yes, we'll come back to that in a moment. Right, in the original construction of Fontaine-Winterberge, they actually naturally get to this thing without taking any perfect closure. So for them, it sort of showed up this way. But in a moment we will prefer to work with perfect fields in characteristic P. Okay, so this statement is, as I said, it's the late 1970s. The first paper on this is from 1979. The proof of this, so there is it's part of a more general statement. I'll just refer to this statement. This version of it already has important foundational consequences for p-adic Hodge theory. We might see some of those maybe already in the next lecture. So I won't go in that direction right now. What I want to do in this lecture is formulate and give some sketch of the proof of as I said, 21st century generalization of this, which puts this in a much broader context and essentially takes advantage of a lot of knowledge that Fontaine accumulated over the years of dealing with this construction. So in some sense, all of the ideas in what I'm about to say are basically already in the early work of Fontaine, but somehow it took until the late 2000s before anyone realized that they could be teased out and put in this way. So we will deduce this more general result. And just like any good idea, it sort of showed up more than once at the same time. So it showed up in some work that I was doing with my former PhD student, now collaborator, Rochan Liu. And then around the same time, it showed up in the original work of Scholze on what are now called perfectoid spaces. So we'll, if you look in the bibliography, whenever I mention a statement there, I give appropriate references in various places. So I mostly won't give the references out loud as I go along. Okay, so how does this generalization work? Well, the idea is to identify the key feature of a field like this that allows you to compare it to some field of characteristic P. And before I tell you what that is, let me make a few basic definitions about fields and absolute values. So I'll refer rather often to the concept of a non-Archimedean field. Let me see if I can spell that correctly. By this I'm going to mean it's a topological field. So it's a field equipped with the topology, and the field operations are continuous. And I want the topology to be induced by skip this word for the moment. So I want the topology to come from a non-Archimedean absolute value. So this absolute value should satisfy the strong triangle inequality. And I want the field to be complete for this topology. So of course, QP is the first example you're supposed to think of. So QP is complete for the p-adic absolute value. And so I topologize QP using that absolute value. Of course, the second example you should think of is this local field in equal characteristic P. But in particular, these are not necessarily going to have discrete valuations. So, something like, maybe I'll write this as C, because I know Udi is going to write C instead of CP here. If you take an algebraic closure of QP, it turns out you can then complete it. Sorry, you can then complete it with respect to, well, there's an induced absolute value which comes from the following remark. If K is a non-Archimedean field, then and you fix, well, you have to choose some, make some choice of the absolute value on it. I mean, the only ambiguity is that, for example, if you took the p-adic absolute value in QP, you could renormalize by, say, replacing all the norms with their 17th powers, and that wouldn't mess up the triangle inequality. So let's say I choose some absolute value on this non-Archimedean field. So it's a basic fact which, for example, if you've learned about local fields, you've seen this argument, but it doesn't depend on it being a discrete valuation. If you have a non-Archimedean field, then the absolute value, any choice of absolute value, will extend uniquely to every finite extension. And so if I take an algebraic closure of QP, so I start with, say, the usual normalization of the p-adic absolute value on QP, then I can extend it to every finite extension inside an algebraic closure, and so I get an absolute value on this thing, but it won't be complete. If you take an infinite algebraic extension, you do get an absolute value on that, but you don't get something complete. So you have to take the completion in order to be what I'm calling a non-Archimedean field. So this is not a non-Archimedean field because I haven't completed it yet. There's another key remark, which is that if K is a non-Archimedean field, and L over K is an algebraic extension, so it's some composite of finite field extensions, but it might not be itself a finite degree, then L, so by the same logic I just described, there's a sensible way to complete L by, well, if I take an absolute value on K, I can extend it to L uniquely, and then I complete with respect to that. So these things will have isomorphic Galois groups. So in particular, I started with QP mu p infinity. So if I want to get into the world of non-Archimedean fields, I can complete that. On this side, we were just discussing, this thing is of course already complete, but when you do Galois theory in characteristic P, usually it's better to work with fields that are perfect, which is to say the Frobenius map is actually a bijection. And so that won't be the case for this thing because T has no pth root. So what you do to fix that is you take this field and you adjoin a pth root of T and a pth root of that and so on. So I'll write this as fp parentheses T to the 1 over p infinity. So this is an infinite algebraic extension of this non-Archimedean field. So now I have to complete it again. Maybe I'll write the hat over here to avoid making a mess. So if I take this field, when I join these pth roots, I do not change the Galois theory at all. So these two fields have the same Galois groups. And then completing, these two have the same Galois groups. At least if you believe this remark. So this remark comes from, well, it uses various things. I give more details about this in the notes. One of the things that it uses is something that I want to point out explicitly because I'll use it again. So one of the no, sorry, let me not. That's correct. Again, the finite extensions correspond. So yeah, I don't have a, yes, this is again an isomorphism of Galois groups that comes from an isomorphism of Galois theories. Yeah, in this lecture, whenever I say two Galois groups are isomorphic, I'm going to mean that actually there's an isomorphism of, the right way to say that is that there's an equivalence of the Galois categories. So if you look at the categories of finite extensions of the two fields, just with, as subcategories of the category of rings, then those two categories should have an equivalence between them. And that will give you an isomorphism of Galois groups as topological groups, but it's somehow more, it rules out the possibility that there are some mysterious non-algebraic homeomorphisms at work. This is not an Annabelian geometry lecture. Well, yeah, I have to, yeah, so from the homeomorphism, what do I need to know that every, yeah, so I need to know that every finite quotient actually comes from a Galois group, but that's true. Yeah, so the information is really in the topology, but if you don't want to think about the topology on the groups, I'm always going to say this in terms of finite extensions. So really, what we're going to do to prove this theorem is provide some identification between finite extensions, or some matching. Yes, it will be an explicit, it's slightly non-canonical, but only slightly. But it is an explicit bijection between finite extensions. Yeah, maybe I should say this will be an explicit construction, if not quite canonical. Okay, so I'm going to put this in the context of perfectoid fields. Instead of working with this thing, I'll work with its completion, and instead of this thing, I'll work with the completion of its perfect closure. And so those two things turn out to have a relationship which can be generalized. So to give that, I should give the definition of what's called a perfectoid field. So what is a perfectoid field? It's a special type of non-Archimedean field. So I guess implicitly I already did this, but let's fix a prime P throughout this lecture. So a perfectoid field is going to be a special type of non-Archimedean field, but I only want to consider fields for which the residue field has characteristic P, right? So if K is a non-Archimedean field, yeah, maybe I should do this notation first. So if K is a non-Archimedean field, I can write OK for the associated valuation ring. So these are the elements of K that have norm at most 1. This doesn't depend on the normalization. And I again emphasize this is not typically a discrete valuation ring in the context in which I'm working. Like here it's obvious that you would not get a discrete valuation, but already for this thing, if I take the completion of this, this already has not a discrete valuation. So this would not be a discrete valuation ring in that case. Well, this kappa notation is going to be horrible on the board. So this is a local ring, so it has a residue field. So we assume hereafter that the residue field of OK has characteristic P. That's the only case I'm going to be interested in. So under that condition, we'll say K is a perfectoid field if, so k is not discretely valued, so I'm going to have to rule out the possibility of taking QP because it will slip through the next condition. But here's the important condition. If I take OK mod P, so this is a ring in which P equals 0. So it has a Frobenius homomorphism, right? The map x goes to x to the P is a ring homomorphism whenever you have a ring for which P equals 0. Now this ring, this is not reduced or anything in general. This will have a lot of nilpotents if I take, for example, k equals c. But nonetheless, it's of characteristic P, and so x goes to x to the P is a homomorphism, and I want this homomorphism to be surjective. So for example, if K is algebraically closed, it is certainly perfectoid. For a trivial reason, it's certainly not discretely valued. If it's an algebraically closed field, it has to have divisible group of values. And this map is obviously going to be surjective because you can take the pth root already in OK. But you don't need to necessarily have pth roots of everything in OK. So if you have a field which is closed under taking pth roots, that's a weaker condition than algebraically closed. That would also work. But you can also take an example like, well, let me not quite take the cyclotomic example first. Let me take a slightly easier example. If I take K to be the completion of QP adjoin P to 1 over P infinity. So I adjoin a collection of coherent P power roots of P. They have to be coherent because this is not a Galois extension. So it's not that like I'm joining all of them. So I adjoin a single pth root of P and a single pth root of that and so on. Then the OK for this, it looks like ZP adjoining all these pth roots of P, and then I complete for the p-adic, complete this ring for the p-adic topology. And then when you reduce mod P, you get something that looks like, well, the first thing goes to something else. So say the pth root of P goes to something that I'll call T1 bar. The P squared root of T goes to something I call T2 bar, and so on. Sorry, this is going to be FP already. I might as well divide by P. And then I have some relations like T1, its pth power it goes to 0. And then T2 bar, its pth power is identified with T1 bar, and so on. And so obviously the pth power map on this thing is surjective because it sends T1 to 0 and it slides the other variables to the left. So slightly less obvious example, I'll let you think about this one yourself, but it's very similar. If you take the cyclotomic extension, then OK, again, is sort of what you expect. It comes from taking ZP and adjoining the pth roots of unity and then completing for the p-adic topology. And then you can make a similar calculation. The only difference is that the T1 looks a little different, but otherwise, because instead of T1 to the P, you have the P cyclotomic polynomial evaluated at T1. But then the other terms look the same. So again, there's a shift that happens when you take the Frobenius mapping on the reduction mod P. Yeah, here I complete the field as well, yes. So this is the key definition. So it turns out that there is going to be an analog of the Fontaine-Winterberge theorem for any field of this form. So what is the corresponding field of characteristic P going to be? So this is a definition lemma. Because you have to prove something, but in order to make this a sensible definition. Oh, maybe I should mention, why do I call this perfectoid? Well, I did leave the possibility that K is of characteristic P. So if K is of characteristic P, then this condition is just telling me that the field has to be perfect, that the P power map is a bijection. So this is meant to be some, this is meant to be some mixed characteristic version of the concept of a perfect field. Okay, so let K be a perfectoid field. So I'm going to do the following thing. So if I take OK, then set theoretically, I can take the inverse limit of OK under the P power map. So this means I take a sequence in which the first term is an element of OK, the second element is a pth root of that, and so on. Now, of course, not every element in OK will actually have a pth root. So you just take the ones for which you can make a sequence like this, and you take all the sequences of that form. So that's a set theoretic construction, but it's not just a set theoretic construction. So it doesn't behave very well with respect to addition, but it does behave perfectly well with respect to multiplication. So this set actually has a multiplicative structure. It's a multiplicative monoid. Okay. And obviously, if I replace something that OK maps to, then I'll get a compatible map. So if I replace OK with OK mod P everywhere, now this is actually an inverse system in the category of rings. So this is a ring, but this is not a ring. So the statement here is that this map of multiplicative monoids is a bijection, is an isomorphism. So this is the lemma part. You have to check this, but it's not so difficult. I'm sorry? That's right. So the unit here is just the one sequence. So yeah, it's an isomorphism of monoids. And so what that means is that this monoid has a ring structure inherited from over here. So there is a natural way to put a ring structure on this thing by bringing it from there. So from 1, this multiplicative monoid acquires a ring structure. So then the next part of the lemma is that this is a perfect valuation ring of characteristic P. So the fact that it's characteristic P is clear because from this point of view, I took an inverse limit of things of characteristic P. So of course I get something of characteristic P. From here, maybe it wasn't so obvious. Well, the reason it wasn't obvious is because it wasn't obvious what the addition was. But if you actually work out what the addition is in terms of these things, then when you do it P times, it somehow gives you 0. So it's clear that you're going to get something of characteristic P. It's also not so hard to see that it's perfect because in this construction, if you want to take the pth root of everything, well, you've basically given yourself the pth roots already. So if you have a sequence and you want to know, well, what sequence would give me pth roots of that? Well, you just omit the final term. And then you get a sequence that gives that when you take the pth power of every term, it gives you back the one you started with. So because I took this inverse limit, I automatically have unique pth roots. So this part and this part are kind of easy to see from here. And the part where you have to do a little bit of work is you have to check that this is actually a valuation ring. Well, let me finish the statement, and that'll put this in a little more context. So the fraction field of this is also relatively easy to describe. So the fraction field of this will have underlying monoid the corresponding inverse limit where you take k instead of OK. So this thing also acquires a ring structure by sort of comparison to this one, and this turns out to be the fraction field of this. And I can tell you what the valuation, what I can give you a good choice of an absolute value to put on here. So let me give this thing a name. So this is Scholze's notation. The Fontaine didn't really have a notation for this. So Scholze's notation for doing this construction is K. This is not a B, this is a flat, like in musical notation. So this is flat. So if you're typing this in LaTeX, it's \flat. So what is the absolute value? Is in fact restriction from K along a map that I'll call sharp, again following Scholze's notation. So, right, this set theoretically, and also multiplicative monoid theoretically, right, an element of this K flat is a sequence of elements of K. So if I take the final term in the sequence, the one that everything else is sort of powering to, that gives me a function. So there's a well-defined function from here, which is the projection, the final projection. And this is a multiplicative map. This, by construction, this is multiplicative. And it turns out that the right choice of an absolute value to take on here is just the restriction of the absolute value function on here, which of course behaves perfectly well with respect to multiplication. And then the lemma part is that it actually does something meaningful with respect to addition, that it satisfies the strong triangle inequality. So that's again something one has to check. So a couple of more important points about this construction. So via the sharp map, if you look at the possible, the range of the absolute value function, it's the same in both cases. So the value groups of the two fields match up. So, and moreover, I can say that OK mod P is isomorphic to OK flat modulo something, where I choose this X bar to have the property that sharp of this divided by P is a unit in OK. Right, this tells me that there is something in characteristic P whose sharp has the same absolute value as P. So if I truncate OK flat modulo that, I get the same, literally the same ring as OK mod P. So essentially what I've done here is in a functorial way, I've taken a perfectoid field and I've converted it into something of characteristic P in a way that preserves some structure, as much structure as I can hope to preserve when I go to characteristic P, which is I preserve the range, somehow preserve the absolute value in some sense, and I preserve the reduction mod P in this sense. So this is the sense in which the K flat is some kind of characteristic P uptar of K. Examples. And so this is it's some sort of exercise to check these examples for if I take the first example of the two over there, if I take QP adjoin P power roots of P, complete that, this K flat looks like the completed perfect closure of a power series field in characteristic P, where T corresponds to the sequence P to 1 over P, P to 1 over P squared, etc. So there's an identification of the K flat in this case with a perfect, the completion of a perfect power series ring where T corresponds to this sequence, which is obviously present from the way I constructed this field extension. So it's slightly less obvious what happens in this case, but in this case, for the cyclotomic extension, it turns out you also get this thing as the flat, as the flat version. But I have to tell you what T corresponds to in this case. Well, let's see. It's easier to tell you what T plus 1 corresponds to. T plus 1 corresponds to 1 zeta p squared, etc. Right, so this can't be T because this thing would not be topologically nilpotent. But if I subtract 1 from it, then I get something that's topologically nilpotent. And so that turns out to correspond to T. So already in this case, you see that the passage from K to K flat necessarily loses some information. That is perhaps not surprising. Well, you can also ask about C flat. We'll do that in a moment. But before I do that, I should mention that, again, there's a terminology here which is not in Fontaine, was introduced by Scholze. K flat is, we typically call it the tilt of K. I guess the metaphor is that you have something which is somehow in mixed characteristics, so it's somehow sticking out of characteristic P, and you kind of turn it down, kind of make it lie flat in characteristic P. So imagine.
So what is sharp map?
In which case? Well, the sharp map, it's a little bit hard to say in general. Like in this case, the sharp of T is P. But the sharp of a general element is actually kind of difficult to write down. And again here, the sharp of T plus 1 is 1, but the sharp of T is a little bit complicated to write down. Yeah, it exists, but it's not so, it comes from some, like the proof of this involves some p-adic limits, and it's not so obvious how to write it down. I mean, you can trace it through and get some representation for it, but it won't be a finite construction. It will involve some infinite process. Okay, good. So to tell you about this, let me give you a key lemma. So this is actually a lemma not about perfectoid fields, but about non-Archimedean fields. But it has an obvious consequence. So K, for a non-Archimedean field to be algebraically closed, I need two things to be true. I need the group of values. I need this not to be the discrete. I need it to be not a discrete valuation. And then for some, or equivalently for any, if I take any element, or even just one element, with absolute value less than 1, I want it to be the case that every polynomial over OK mod x has a 0 in OK mod x. So for every polynomial with coefficients in OK mod x, there should be some value of OK mod x where the polynomial evaluates to 0. Now, of course, this is not a field, so it's not that a polynomial of degree n has exactly n roots. It'll have lots of roots. But I want there to be the case that every polynomial over OK mod x, every non-constant polynomial, I suppose I should say, positive degree, every polynomial of positive degree should actually have a 0. So this is obviously true if K is actually algebraically closed. And so the content of this statement is that if you have this properties, then K is algebraically closed. Basically, the way this works is if you start with a polynomial over K, well, I can renormalize it. So it's a polynomial over OK. And then I can construct roots using this property and some sort of successive approximation. I give a few more details in the notes about this, but let me just leave it at that for the moment. This is some kind of topological property because K is complete. So this has the consequence that these properties are both invariant under tilting. So if K is a perfectoid field, then K is algebraically closed if and only if K flat is algebraically closed. Because on the side of K, the value group is actually divisible, so it's certainly not going to be discrete. It's already not discrete from the definition of a perfectoid field, but that's also true on the tilt side. And then this property is precisely the thing that I need to know is that, I'm starting with something, if I start with K being algebraically closed, then I get that this truncation has this zero property, and then this truncation has this zero property, and then I can go backwards and say that K flat is algebraically closed, or vice versa. So if you read the treatments, the various treatments, like Scholze's paper or the papers of mine that I give in the references, this is stated as a lemma about perfectoid fields, but really, it's not a lemma about perfectoid fields, it's a lemma about fields with non-Archimedean absolute values that you just happen to be using in the perfectoid case. You're using the fact that this tilting construction preserves, of course it preserves residue fields because of this, but it's preserving much more than that. It's preserving these truncations. Remember, these things are not discretely valued, so this is, this is in some sense still has infinite chains of ideals in it. Okay. Right, so now I can state this theorem that generalizes the theorem of Fontaine-Winterberge. Actually, maybe before I do that, I should just mention that, from what I just said, C flat, whatever it is, it's something algebraically closed. It'll follow from the next thing I'm about to say that it's actually a completed algebraic closure of the power series field in one variable over Fp. And that will be a consequence of the following statement. That K and K flat have isomorphic or homeomorphic homeomorphic Galois groups, and this will follow from some more precise statement, namely, so first of all, if K is perfectoid, every finite extension is also perfectoid. If you have an easy way to see this, please let me know. I don't know an easy way to see this. It will come out of the wash from the following argument. And once you know that every finite extension is perfectoid, you can tilt those, and then you can say that there is a correspondence of finite extensions given by, if L is a finite extension of K, then L flat is a finite extension of K flat of the same degree, and this matches up. All the finite extensions on both sides occur in this bin. So I claim this isomorphism of Galois groups is coming from an identification of finite extensions, which is quite explicit. Now, I said this was not quite canonical because, for example, if you take the cyclotomic extension here, there is a choice here because, well, there's a choice in which coherent sequence of p-power roots to use. And so that is basically the entire ambiguity in the Fontaine-Winterberge case. So, yeah, so there is an ambiguity because there's some choice to be made of which thing is t, but
where was that choice used?
just to define just to make an identification, to define this identification. So if you don't actually choose this identification, if you just leave it as k flat, then it's canonical. So the point is that you shouldn't have chosen an identification. Yes. So yeah. So if you have a perfectoid field which is itself a finite extension of something else, then that something else will also be perfectoid. Yeah. Well, maybe we might even see the proof of that. Not sure I'll have time for it, but implicitly it will sort of come up. Okay, so I have less than 10 minutes to say something about this. So let me give you the outline of the proof of this, which uses this lemma, and then I'll start talking about what goes into the proof of that. And in case I run short, this is something that I can postpone into a later lecture. But I want to at least show you the outline of why this is true. So outline of proof. Right, so it looks like the hard part is to see that every finite extension is perfectoid, but in fact, the proof I want to describe, I don't directly prove that. It shows up along the way. So the idea is to instead of talking about tilting, which is the operation to go from a perfectoid field to something in characteristic P, I want to talk about untilting. So the idea is that you use Witt vectors to show that every finite extension of K flat is the flat for some finite and perfectoid extension of K. So you only worry about those finite extensions which happen to be perfectoid, which a priori is not all of them, and you show that every finite extension of K flat is L flat for some unique up to, in the appropriate sense, extension of K. So you show that in other words, you have a functor from finite perfectoid extensions of K to finite extensions of K flat. You're trying to show that that's an equivalence. So first you show it is essentially surjective. That everything shows up over here, and then that would give you a correspondence like this. It's easier to see that it's fully faithful. So that would give you a correspondence like this, except that a priori there might be finite extensions which are not perfectoid, but somehow this rules that out. Then use the algebraic closure, use the algebraically closed case to rule out existence any further non-perfectoid extensions. Why does that work? Well, so first of all, this lemma is a special case of this, because it says in particular if one of these Galois groups is trivial, then the other one is trivial. So something being algebraically closed, since we're talking about perfect fields on the characteristic P side, in either case, being algebraically closed is precisely the same thing as the Galois group being trivial. So that's certainly contained in here, but why would this be enough given this? Well, if you had some, if you take all finite extensions of L flat within some algebraic closure, and each of those can be raised to some finite perfectoid extension, some compatible way, then you have this algebraically closed field in characteristic P, and you complete it, then it will be the tilt of the completion of the tower of finite extensions. So you get some tower of finite extensions, which when you complete it, gives you something algebraically closed. And so, and then there's another lemma that maybe I should have mentioned about non-Archimedean fields. If you have a tower, right, so maybe I should just mention this lemma. I sort of mentioned half of this, but I need the other. If K is a non-Archimedean field, L is an algebraic, or maybe I did mention this, but let me emphasize it by saying it again. L is an algebraic extension. Well, what I said before is that L and L hat have the same Galois group. So this, but I'm going to use the special case of that L is algebraically closed if and only if L hat is algebraically closed. So what I'm saying is if you take all the finite perfectoid extensions of K, the completion of that gives you an algebraically closed field, so that by itself gives you an algebraically closed field. And then, okay, so I have a cofinal collection of finite extensions that are perfectoid, and then I guess you have to use the thing that Sujatha asked about, which is that if you have something trapped, well, you use something slightly less. You need to know that if you have something trapped between two perfectoids, if you have a finite field extension where both things are perfectoid, then everything in between is perfectoid. That will actually follow from the thing that you asked about, which will come out of the analysis of Witt vectors, which I won't give in detail right now, but let me just give you a preview of that. But I can give you the summary of how the construction of these untilts works. So the idea of the construction of these so-called untilts is you identify, if K is perfectoid, then there's a natural surjective homomorphism from the Witt vectors of OK flat back to OK. So yet again, this is a construction that was introduced by Fontaine. He called it theta. Yeah, so I'm trying to construct L given, so I have something which I think is an L flat. So I have a finite extension of K flat, and I would like to realize it as an L flat. So that's the tricky part. And so the idea is to give a general understanding of how do you take a characteristic P field and realize it as the tilt of something. You want to classify all the ways that something can occur as a tilt, because we've already seen the same abstract field can occur as a tilt in multiple ways. So we want to somehow understand what information is needed in order to construct something which tilts to a given target. And so the key proposition here is that, well, once you construct this map, so I'll say a little bit more about constructing this map maybe next time. I don't want to end with a definition, so I'd rather kind of finish at a point where I've given you a preview of the next thing that happens. So proposition, there's always a surjective map like this whenever you start with a perfectoid field. So for the evaluation ring of any perfectoid field shows up as a quotient of the ring of Witt vectors of the corresponding valuation ring. And so what I'd like to show is that the kernel map is, on one hand, principal with generator of a special shape, it's what Fontaine calls a primitive element. And then conversely, given F, a perfectoid field of characteristic P, which means it's a non-Archimedean field, which is perfect and not trivial. Well, it's a non-Archimedean, this is just a fancy way of saying, i.e., a perfect non-Archimedean field of characteristic P. Given F, every quotient of W of 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 this shape, meaning once I tell you what kinds of elements that can occur as generators of this kernel, then every quotient by such an ideal will occur from some perfectoid field, arises from some field K and an isomorphism of its tilt with F. Some perfectoid field, yes. So modulo telling you what the definition of a special generator is, I can classify all possible ways for a field to tilt to F, because they all occur as quotients of the Witt vectors of F. And then how will that help? Well, that will help because then for L, say for E, a finite extension of K flat, what you do is you take the Witt vectors of OK flat and tensor, you take the Witt vectors of OE, tensor over Witt vectors of OK flat with OK. This will be OL, where L is a finite perfectoid extension of K with L flat isomorphic to E. And the reason is because if I start with, the kernel of this map is going to have some generator of some shape. When I extend, if I sort of extend scalars to here, I'm still going to be dividing by that principal ideal. And so this will again be, this will fall into this case. So I'll start with a generator of a good shape, and I'll just use that same generator, replacing K flat with this larger extension, and that will give me a perfectoid field, and that will be the one that tilts to E. So that's somehow the structure of the proof, modulo understanding where this map comes from and how its kernel looks. So what I owe you in a future lecture, either tomorrow or possibly the next day, depending on how we organize things, is the construction of this map and where it's and what its kernel looks like. And that will get us naturally moving towards an understanding of how the different untilts of a given field are related, and that will point us in the direction of Fargue-Fontaine curves, which we'll see in some of the other courses as well. Yes? Well, I claim this surjection is somehow natural. I haven't told you what it is yet. It's characterized by the fact that if you take the Teichmuller elements in here, if you restrict this along the Teichmuller map, you'll be getting a map from OK flat to OK, and that will be the sharp map. So that will be so maybe I'll just write, if you precompose with the Teichmuller map, which is written in brackets, you're getting sharp. And that will uniquely pin down this thing. That's why this L will be unique up to unique isomorphism. That's right. I'll say more about this next time. Well, I haven't told you what the definition is. So there's a certain condition on elements of this Witt ring, which is what Fontaine calls primitive. And so this is going to say that every primitive element defines an ideal, the quotient by which gives you an untilt. So next time I'll tell you, or maybe the time after, I'll tell you what that that shape actually is. No, I'll do it next time. All right, I'll stop there.
Okay, if there are none, let's thank speaker again.